Okay, this is lecture 9. So in the previous lecture, in the last slide, we were thought about how can we calculate the mobility of our electron. For example, if we consider a mobility is written as just mu, and also we can think about different mobility values limited by only one scattering mechanisms. For example, we can define something like a phonon limited mobility or impurity limited mobility. In calculation, actually it is not that difficult to calculate this number, but in reality, how can we quantify these quantities? So these quantities can be obtained by, for example, if we are interested with phonon limited mobility, then we prepare a sample with very low impurity density. Then we can guess that impact of our influence of our impurities are minimized. So that's the way we characterize phonon limited mobility. And how about this one? So this one can be also obtained by considering the case where we have a lot of impurities. So these kind of things, individual components of mobility can be calculated. After that, we take this kind of inverse sum I, that will be the overall inverse mobility. Of course, although I have shown only about phonon limited mobility and impurity limited mobility, but we can think about other different scattering mechanisms. So we can have many other ones. What? I have no idea. And another one. So if you just add more and more scattering mechanisms in your consideration, then just please add those limited mobility to the inverse sum. Then what will happen? Always that each of them will contribute a positive number. So overall, this positive number will increase. When you have more scattering mechanisms, then always this inverse mobility will increase. What is it? So your overall mobility is always decreased when you have more and more scattering mechanisms in your system. So that is typically called as Madison's law, and as I told you before, this is not very exact. So in a microscopic sense, that is not that like a rule or law. However, for as a practical purpose, it is always okay to use this Madison's law. So now let's go to our next topic about energy. So please note that mobility, typical quantity we call mobility, is related with the relation between average velocity and applied electric field. So we have of course something like this, whether positive or negative. So it is related with the velocity of our electrons or holes. However, the velocity is not the only quantity we have to care about. Also, we have to care about the energy of our electron. For example, if we take the average energy of our electron, then what is it? I mean that, of course, you may say there are many different electrons. For example, this is the distribution function and this is energy. Then of course, let's say that this is EC and if we adopt Boltzmann statistics, then yes, that will be the occupancy. So you know, it is in between 0 and 1, and 1 means that the state is completely filled by our electrons, and 0 means that the state is completely empty. So distribution function always show, or at equilibrium, it always shows this exponential decaying behavior. So then what will be the average energy? What we can do is, in order to calculate average energy, we must do this kind of job. So energy integration, and here we have density of state and the distribution function at a given energy. So if we just perform this kind of thing, what was the answer? The answer was, when you just do this job, then it will give you the electron density. But our purpose right now is not to calculate electron density, but calculate average energy. Then what you do is, instead of just taking or integrating this quantity, so this FD times the density of state means that how many states are there and how much that they are occupied. That information can be obtained by this product. But if we multiply another factor, E, energy, then now it can give us how many electrons are there and what is their energy. So now we can define this kind of integration. So now think about this one. The upper part will give you certain quantity corresponding to energy multiplied certain electron density, and this lower part will give you just electron density. So you know, here we have energy times electron density, and lower we have just electron density. They can be cancelled out, and we have some quantity corresponding to the average energy. So that is obtained by this operation. So let's come back to our graphs shown here. If we have to calculate this thing, so average energy, what we have to do is, first of all, consider the distribution function that follows exponential decay as a function of energy. After that, also we have to consider this density of state, but fortunately we have all information about density of state. How does it look like? It just looks like a function which is proportional to square root of energy. So we can calculate this one. This follows D and this follows F. Finally, now we can consider this energy, but energy just linearly increase if we consider not just energy but E minus EC in order to quantify the kinetic energy. Then we can calculate it this way. So are you with me? So of course E here, E means the total energy considering both of potential energy and kinetic energy. However, EC, so conduction band minimum, is the energy of our electron whose velocity is quite close to 0. So we can treat this E minus EC quantity as a realization of kinetic energy, K, or sometimes written as T, whatever. So now once we know the distribution function and density of state, then we can calculate this energy. So typically speaking, if we apply very low electric field, this is electric field and that is written as volt per centimeter. So here you have 10 to the 3. 10 to the 3 is corresponding to 1 kilovolt per centimeter. As I told you in the previous lecture, 1 kilovolt per centimeter should be regarded as a relatively low electric field. In this case, actually energy that is not deviated from our low or equilibrium value. However, here we have 10 to the 4, that is corresponding to 10 kilovolt per centimeter, already quite considerable electric field. Then what happens? So now you can observe the average energy of your electron gas or whole gas is slightly deviated from the equilibrium value, and if you go to 100 kilovolt per centimeter, so as I told you, 100 kilovolt per centimeter should be regarded as quite high in terms of lateral electron transport. In this case, you can see that energy is quite high. Please note that this x-axis, the lateral axis, is written in its logarithmic scale, and also this y-axis is vertical axis is also written in its logarithmic scale. So here and there yes, so here we have 10 times the difference, and here we have also 10 times the difference. So it is quite a significant increase of our electron energy. So why they are becoming a highly energetic particles? So it is quite easy, because when you apply your high electric field, your electrons are accelerated. Then in average they are getting faster and faster, so their energy or kinetic energy, this or that, whatever, this becomes quite much significant compared with just average one. This one is corresponding to just orders of kBt. So you know, this is corresponding, kBt is just 25 milli electron volt. However, if we accelerate our electrons, then it can have a much higher energy than that. Okay. So please have a look at energy. The average energy increases when the electric field increases. That is quite much understandable. And the second, please try to read the second line. Increase of average energy is a reason of velocity saturation. What is velocity saturation? Up to now, we have not talked about velocity saturation. From now on, I will talk about velocity saturation. Maybe you feel a little bit weird, the confusing between different concepts. So saturation, what is the saturation here? In the previous lectures, we have thought like this. Electric field is closely related with force. So if we apply constant electric field, it means that we are doing the constant acceleration. So we expect that velocity is increased indefinitely. However, that is not the case, and eventually we have final certain terminal velocity. So this is related with our scattering mechanisms. However, please note that this is nothing related with the phenomena called as velocity saturation. So this is just terminal velocity, although I have to be careful because terminal is also used for our semester in different context. So let me just say there is certain velocity, but this is not related with velocity saturation. When we say velocity saturation, here we have something like this. Here we have a velocity, the average velocity, it's absolute value, and here we have electric field. Of course it's absolute value. Here we have certain relation, and that is called as velocity saturation. So don't be confused with this phenomena, terminal velocity and velocity saturation. Already we are assuming that electrons or holes velocity does not increase any further, so we just assume certain relation like velocity as a function of electric field, and that linear relation does not hold. And if we say the linear relation holds forever, then if we go to very high electric field, then we expect very high velocity. So for example, if we say this is the case for 1 kilovolt per centimeter, if the velocity is given here 1, 2, 3, 4, then we expect that 10 kilovolt per centimeter, we expect such kind of behavior, our whole velocity. Then how about this? If we go to 100 kilovolt per centimeter, what we can expect is now it is also 10 times higher velocity. And if we go to 1 megavolt per centimeter, it goes another 10 times higher velocity. But in reality, if we just measure the electron velocity as a function of applied electric field, in this part we have some deviation from linear relationship between mobility and electric field. And if we go to certain level of electric field, then eventually velocity is just saturated. That's the reason why this velocity called as saturated. Okay, so don't be confused with this one. So in our previous lecture, we just assumed the linear relationship between velocity and electric field. That was due to scattering itself. However, that relation happens not only in high electric field, but that happens also in quite low electric field. Only when we go to very high electric field, then now velocity, this terminal velocity does not increase any further, and that is saturated, and its value is about 10 to the 7 per centimeter per second. That is the one I wanted to say. So although the order of presentation is a little bit inverted, however, what I wanted to say is this increase of energy is closely related to the phenomena called as velocity saturation. If you apply high electric field, what you expect is, since our acceleration becomes stronger, so maybe the velocity, our electron velocity, will be increased. That is our usual assumption. However, please have a look at this one. This graph shows the energy versus scattering rate. So how frequently the electron or holes are scattered by our scatterers, that is shown here. And for example, this high value of this scattering rate means that our holes are more frequently scattered by other scatterers. For example, if we think about this one has relatively low value of scattering rate. It means that if your hole is located at this energy range, it is not that much scattered. But if one hole is quite lucky and accelerate and eventually go to this high energy level like 3 electron volt, then every surrounding scatterer will try to hit this lucky hole. I mean that if you have nothing, then thieves are not that much interested to you because there's nothing to be robbed from you. However, if you have a lot of things, then maybe there will be more attempts to steal something from you. So simply speaking, now think about this one, the journey of an electron. Yes, starting from quite a low electric field, it is located just bottom of our band structure, and its kinetic energy is quite low. However, we have applied high electric field. Oh, now it is quite lucky and it is accelerated. Sometimes it gains some energy, after that it loses its energy, but again accelerated. That kinds of motion will happen inside the K-space. And let's assume that this electron is quite lucky and eventually getting more and more energy. Then what will happen? Compared with this low energy age, if it goes to 1 electron volt or even higher, then it has much higher chance to be scattered. So that's the reason why the velocity saturation occurs. So think about this one. So relatively low electric field, relatively high electric field. In this case, our electron gas does not get much energy. Its energy is just so scattering is not that frequent, so it has a certain velocity. However, in this case, high electric field, what happens is, if we apply high electric field, it becomes quite a high energy in average. After that, it just activate more frequent scattering events, so it is frequently or more rapidly cooled down to our original state. So that's the reason why here, since we have more scattering, although they have certain higher acceleration, but their velocity is not that high. So please think about this one. So when you have a look at these graphs, you must understand this graph. The graph just shows how frequently our holes are scattered and how frequently our electrons are scattered. That is drawn. And please note that the shape of individual graphs. So you must understand this graph is just follows the density of states of your conduction band. Also, this curve just follows the density of states of your valence band. Simply speaking, the scattering rate, how frequently our electrons and holes are scattered, is almost solely determined by what? solely determined by the density of state. If you go to high energy level, then you have plenty of rooms. So that's the reason why your electrons and holes are experiencing so many scattering events. If your electrons and holes go to the low energy level, then there are relatively small number of density of states. So that's the reason why the scattering rate is quite much reduced, and yes, just you have usual value for your velocity. Okay, so why I'm spending so much time about this one? Because this velocity saturation is actually one of the most important thing we have to care in the realistic application. Somebody can say that, oh, this material has quite a high mobility, blah blah blah. However, all of this kind of thing is always measured at quite low electric field. However, when you try to use some material into your realistic application, like logic or any kind of memory application, then usually what you apply is quite high electric field. It is quite natural, because if you apply low electric field, then the current will be quite low. If you apply high electric field, then current will be increased. What is related with high performance application? Of course, in order to achieve high performance, more current conduction, you have to apply high electric field. So please have a look at this one. I think that can be a best example for you. Here you are now looking at two different species taken from both from silicon. One is called as electron and one is called as hole. And everybody in this room understand electrons has some tendency to show higher mobility than hole. So if we compare electrons and holes, then maybe you feel that electron is better for example, since it has higher mobility. However, please have a look at this graph. If you go to eventually to the high electric field region, then what happens? In this case, actually their difference is not as high as the one shown here. Here you can see almost 3 times differences in their mobility. However, that is not that important. Actually, they are becoming quite close to 10 to the 7 centimeter per second. Not that much different between electrons and holes. So, of course, mobility is one of the most important quantity. Yes, in order to quantify the electrical property of a certain material, we should be very careful about mobility. However, once that is passed, oh, okay, this material has a somewhat desirable mobility value, then next thing we have to consider is what happens if we accelerate it further. So now please think about this one. If we have extremely good material which has 10 times higher mobility than our silicon, then what will happen? Please try to draw. Here, for example, in this case, it is corresponding to almost 1400 square centimeter per volt per second. In this case, you have this one. Now let's assume another very good material which has that its mobility value is quite close to the 10,000 square centimeter volt second. Then please please try to draw the voltage versus electric field relation in this graph, please. What you can see is, okay, if we have this quite a high value, then for same electric field, same low electric field, then we will have, instead of this slow electron, we will have this point. Because you know mobility is so high, then what will happen to our electrons beyond this level? Let's assume that although we have quite high mobility, but saturation velocity is still 10 to the 7 centimeter per second. Please try to draw it. Then what you can understand is its behavior will just follow this. Of course, not this exactly piecewise linear, but roughly we will have this kind of behavior. So what is it? Although it starts from quite high speed because it has a higher mobility than that, but eventually when we apply high electric field, then the velocity is determined by not by mobility but by the saturation velocity of a certain material. And unfortunately the level of saturation velocity is more or less just 10 to the 7 centimeter per second at room temperature. Of course, I would say that there are other materials whose saturation velocity is not exactly 10 to the 7. Some materials have 2 times 10 to the 7 and some materials have 3 times 10 to the 7. Oh, twice or 3 times higher than silicon. Sounds great. However, it is not like hundreds times higher or thousands times higher than silicon. So please note that mobility is the quantity we can exactly obtain when we have low electric field. However, our actual application is not related with low electric field case. Usually we are interested with high electric field case. So saturation is so important thing. So please, when you do your real job, always please consider this velocity saturation effect. And yes, so now we have this form. So simply speaking, beyond, for example, roughly speaking, 10 to the 4 here, that is corresponding to 10 kilovolt per centimeter, then maybe this one shows significant deviation from our linear expectation. If our velocity just linearly increase, then it is deviated. So how can we model this, or how can we describe this behavior? Now we understand that happens from the increase of our scattering rate. If our electrons and holes are heated up, having higher energy, then higher energy means more frequent scattering. So that's the reason why our saturation velocity is saturated. Although we understand that one, but still there is some issues. How can we model this one? So velocity and electric field, if we say linear relationship, then it is quite good. Say that, yes, that will be the best one if we have a constant relationship, and that really happens when we have a low electric field. But unfortunately, now we understand in this case this is no longer the case for holding the linear relationship. How can we solve this problem? So people were so clever, instead of assuming this global constant mobility, they just introduce some phenomenological form like this. Just to consider velocity divided by applied electric field. That is nothing related with mobility in reality. So actually mobility should be defined on this low electric field region, and just should be extrapolated up to this high electric field region. However, since it is failing too drastically, instead of that, people just takes two numbers, velocity, measured velocity, and applied electric field. Their ratio is sometimes defined as mobility. So also this kind of notation is widely used, so it is challenging to distinguish two different concepts. Mobility in rigorous sense should be regarded as just a linear relationship between your velocity and electric field at low electric field limit. However, in many cases, people just say that mobility defined at high electric field. Conceptually, it is not that much rigorous, but they just take the ratio between velocity and electric field that is shown here. Then please try to do something. Let me just give you more. Now, from now on, please think about your mobility. Now let's assume that if we go to higher and higher electric field, then velocity is just a constant. And please try to calculate your mobility, effective mobility at this point and that point. Please, between this and that, we have 10 times difference of electric field. Then if we calculate the mobility, just the ratio between velocity over electric field, then what will happen? If we adopt this thing, velocity is always 10 to the 7 centimeter per second. However, if we have 10 times a higher electric field, then electric field will be increased 10 times and calculated mobility will decrease 10 times. So simply speaking, if we introduce this phenomenological mobility into our scene, then what we can see is, okay, if we go to high electric field, mobility drops down and it just follows the limiting form like 1 over electric field that is obtained. However, once again, please note that this is nothing related with actual mobility. The mobility should be defined at low electric field region, and this is just a description about your voltage versus electric field behavior. So in order to describe this one, now they have this they means that some researchers introduce this kind of description. So here and there, the measured electron velocity or measured hole velocity is written as this form, and here V sub s, that is corresponding to saturation velocity and quite close to 10 to the 7 centimeter per second. Now let's consider two different limiting cases. One case is electric field is quite low. Then what will happen to our system? If we adopt this kind of expression, and when you go to quite low electric field, then this lower part becomes extremely small. Then what is it? Then overall this ratio will become quite high. So compared with this fixed number 1, which one will be dominant? Of course this ratio will be dominant. So let me just write down in this way. When here we have 1, previously we had 1, but that's just neglected. Then now we have just square over this ratio and take square root. So are you with me? Then what happens? In this case, this square and square root, they are cancelled out to each other. So eventually what we will get is Vs divided by E not electron and electric field. That will be obtained. What is it? This is nothing but when we go to low electric field, velocity just proportional to the applied electric field, and here we have a certain term corresponding to the mobility of our electron. So that is shown here. That was a limiting case for our electric field, negligible electric field. Instead of that, now let's go to quite a high electric field. Then what will happen? Now if our electric field goes very high value, then actually this ratio does not contribute any further compared with this number 1. Now this ratio become really negligible, so our electron velocity will approach it to the saturation velocity. So now you understand, once we adopted this kind of expression, then we can just describe the experimentally obtained data. So if you ask me why we have to have this form, then actually there is no fundamental reason we have to have this form. This is just expression to describe experimental data. And please have a look at the difference between electrons and holes. They look quite similar, but here you can see the lack of numbers. For example, previously we had for electrons number 2 and number 0.5. So 2 and 0.5, when they are multiplied to each other, then we have a unity. However, now we have just number 1 and number 1. Why do we have different values? It is because the shape of this approach. So since the transition from this perfectly linear to perfectly saturation part are different, that's the reason why we can introduce different factors to describe the degree or the speed of approaching to the saturated velocity. Okay. So today I have spent almost more than 40 minutes to describe about velocity saturation. Why it is important? why it happens, how it is different from other mechanisms have been already discussed. After that, I wanted to say other scattering mechanisms. However, these other scattering mechanisms are so important, so I think that I cannot finish it within one slide. We will revisit this effect once again later when you consider MOSFET. This is nothing related with bulk material, but when we introduce MOSFET structure, then we have to introduce other scattering mechanisms. So that is shown here. This graph is so famous, therefore you have to be getting familiar with these graphs. That is usually called as so-called universal mobility curve. Please have a look at this graph. And this graph simply draws the mobility as a function of electric field. So here electric field, so of course electric field has a direction. So this is when we say that electric field, this is vertical electric field. I mean that. So let me just explain a little bit further. Here you have your electron, and when you apply the electric field to this way, then your electron will move that way. In this case, you say that this electric field is applied along lateral direction. Why it is called as a lateral direction? Because this term was originated from our MOSFET. Our MOSFET has certain form like this. Here we have a lot of electrons, and when electric field applied in that way, your electrons are moving in that way. Usually in MOSFET, this direction is called as a lateral direction, and this direction typically called as a vertical direction. That's the reason why we call it as lateral direction. So more academic term will be longitudinal direction, the direction which is aligned to its movement, that is longitudinal. But anyway, such kind of terms are used frequently. So anyway, up to now we have thought about the velocity, we have thought about the relation between velocity and electric field, but it's a lateral component. But in this graph, when we say electric field, this is no longer the lateral direction. That is the direction, the electric field perpendicular to its movement. I mean that although electrons are moving in this way, now we are considering certain certain electric field heading in that way. This is the x-axis of this universal mobility curve. I mean that I'm just let's think about this one. So let me just there is sea and ground, and there is a wall, and one guy is just running and jogging. And today it is quite windy, so we have quite a strong wind in this direction. that is the typical case. That is an analogy with our case. Here, one guy is corresponding to our electron. It is moving. Its movement is along this wall between C and ground. However, the force is applied not to the direction of this running man or running woman, but it is applied to the perpendicular case. So think about this one. No windy day. It is quite comfortable, and strong windy day. What will happen? Although direction of wind is nothing related with the direction of jogging, however, in order to just keep, or in order to just being alive, this guy should spend some energies to against the adjust its or his or her body to this track. So maybe I expect that if we have high or strong wind, then maybe the average velocity of this running guy will be drastically reduced. So that effect is shown here. Although our electron is moving this way, but our electron experiences certain electric field which just push it to the wall. Then maybe its speed will be degraded significantly. Running, but somebody is constantly pushing me into this wall, then I have to work against that force and keep the movement. That is the vertical direction dependence, and it is also quite important. Why it is quite important? It is because the basic mechanism of getting electrons into our MOSFET channel. So let me just explain a little bit further. I assume that everybody understands the structure of MOSFET. So when we have MOSFET, here we have a good wall called as silicon dioxide, and here we have silicon. And the basic mechanism to get the electric channel is just to apply really strong electric field. So our electrons are originally located here, but that was actually pushed into this silicon dioxide silicon interface. The only reason why our electrons are found here is the existence of really strong electric field. Without this strong electric field, we cannot gather sufficient number of electrons. So they are closely related. Yes, if you want to get more electrons, then you have to apply strong electric field. If you wanted to have almost no electric field, no electron, then you may apply quite a small electric field. So therefore, whenever you wanted to make a good electrical conduction, you need a lot of electrons. Unfortunately, you have to apply quite strong vertical electric field. Then what happens to the mobility of this electron? Unfortunately, here this x-axis is corresponding to the vertical electric field, and our electron mobility shows really drastic decrease when high vertical electric field is applied. So think about this number. Here, this number is just 100. Where can you find your ideal value? 1400. 1400 can be found here. So are you with me? This is corresponding to 1400 100 square centimeter volt per second. So in reality, such kind of a value can be never achieved by our realistic device, because there are so many scattering mechanisms, and unfortunately actually this is the actual range of our application. We are using our device not in this range but in this range, so we have to be careful about the real mobility which can be achievable from our realistic device. Okay, so since this issue is too important, so this short discussion cannot cover all kinds of phenomena, so we will revisit this effect once again when we consider MOSFET. But for a while, just think about this one. Today, up to now, we have discussed about bulk mobility. The major effect we have to consider is phonon and impurities. However, they are just to define bulk mobility. Bulk mobility means that if you just have a quite macroscopic sample, large sample, homogeneous sample, then that will show such kind of mobility. However, in reality, you have to introduce silicon dioxide on top of your silicon and apply strong vertical field and something. So there are more to be considered. Although our lecture is highly focused on the silicon material, however, this slide is an exception. In this slide, we are considering gallium arsenide case. Gallium arsenide or similar materials shows quite interesting behavior called as negative differential mobility. So now we have to understand the terms like this one. What is differential mobility? Then we have to understand, let me just summarize in this way. In rigorous sense, the mobility should be the relationship between these two quantity and valid at low electric field. So that is the most rigorous one. However, conventionally, we introduce a concept of mobility which is phenomenologically obtained by just taking the ratio between E and velocity and electric field. This is typically called as mobility, although not that much rigorous. But what is now differential mobility? Here differential mobility is something like this. Here we have the relation between velocity and electric field, and we just take these values and calculate the ratio. But instead of that, differential mobility just do something like this. Treat our velocity as a function of electric field and take the differentiation. So let me just come back to our example. For example, in this case, if we take differentiation, then you can find that difference or the derivative are different at each point. Or directly consider this gallium arsenide case. If we take differentiation, what is the derivative? Derivative 0. Please consider this part. What is the derivative? Derivative positive. And please consider this part. What is the derivative? Derivatives gives us a negative value. So differential, this is differential mobility, and differential mobility is not frequently used in our characterization. If you are doing some simulation job or modeling job, then usually you just consider a typical mobility, because more or less you are interested with just velocity. However, the differential mobility means just derivative of your velocity with respect to the electric field. And if you consider silicon material, then if I just overwritten over these graphs, then maybe you have something like this. This is the, sorry about my not very accurate drawing. So first of all, the saturation velocity is just 1, so we should be limited in this part. And silicon has much lower mobility, so compared with this one, we have this kind. So usually silicon, we expect such kind of behavior. However, in the case of our gallium arsenide, it has higher mobility, so at low electric field region, it just goes up quite rapidly. After that, it reaches its maximum velocity. After that, it is not saturated, but it is just going down. And after that, it is approaches to a certain saturated value. Quite interesting and weird. It sounds quite weird. Why we have, so simply speaking, in this electric field range, although you have increased the acceleration, actually speed is reduced. So you applied even higher electric field and expect that at least its speed is not decreasing, but here you can see that decreasing. Acceleration is decreased terminal speed. That is shown in this gallium arsenide material. This is quite interesting and not that easy to understand from our current discussion, and it can be understood by showing this band structure. And this is a band structure of our gallium arsenide material. Of course, this is a valence band, and this is the conduction band of gallium arsenide material. And where can you find the lowest energy level? You can find the lowest energy level here. For example, if this is 100 direction, then previously in our silicon material we had the minimum value occurs here. Do you remember? So I told you several times about this line is called as a delta line, and here we have 0.85 over the distance between gamma and X point, and this is corresponding to the location of a silicon conduction band. However, in the case of our gallium arsenide, the minimum point does not appear in this near X point. It appears where? Exactly at gamma point. So therefore gallium arsenide is called as direct semiconductor or direct band gap. It has direct band gap because the location K point for having EV and K point for having EC they are identical. At the same K value, we can find both of conduction band minimum, valence band maximum. That is called as a direct band gap material. However, in the case of silicon, although valence band maximum is found at gamma point, however, conduction band minimum can be found on the delta line. So this one, we have no direct relation between these 2 points. So this is called as indirect band gap material. But anyway, gallium arsenide has the lowest value at gamma. So if we have electrons in the gallium arsenide, so at low electric field, of course, we can find our electrons only in this gamma valley. And the second lowest one can be found in this point, and this point is called as L valley because it is located, its minimum value is located so-called L point. I want to say that also silicon has L valley. However, silicon L valley is far away from its global minimum value, so we can completely neglect the contribution from this L valley. But in the case of silicon, in the case of gallium arsenide, the difference between this gamma valley and L valley is just 0.31 milli electron volt. Yes, this is not that small. This is more than 10 times of our summer energy. However, now we are considering high electric field like 10 kilovolt per centimeter. Then what will happen? If we apply high electric field, then our electrons are getting heated up. So now we can see that some electrons get sufficiently high energy. Once its energy is beyond 0.31 electron volt measured from this minimum value, then for these electrons, both of gamma valley and L valley can be accessible. So some of them just move into this one because it is almost empty and it is populated. So there occurs certain movement or transition from gamma valley to L valley. So what? Yes, some electrons are moving from gamma valley to L valley. So what happens? It is related with the curvature of our band structure. So do you remember? We have introduced something like a concept of inverse mass. And inverse mass was obtained from what? Inverse mass was obtained by second derivative of our energy with respect to the K value. So please try to consider which one has higher curvature and which one has lower curvature. So you know that this one, for small difference, energy is highly increasing, and for this guy, for small K deviation, energy does not increase fast enough. So simply speaking, this one is corresponding to heavy mass. This one is corresponding to relatively light mass. So what happens? So previously we had light mass for electron conduction, but when we apply high enough electric field and some of our electrons are just transit from this low mass case, light mass case to high mass, heavy mass case. In this case, now they becoming slower, and starting from this fast one, they are getting slower. Are you with me? Because you know, we are just considering the same energy, and when we have the same energy, if we have a small mass, then in order to get energy, we have small velocity. Oh, sorry about that. This is not the case. Energy is given by half of m times velocity square. So if we have a small light mass, then velocity should be large to have a certain energy. However, if that is moved to transit to heavy mass case, then in order to get the same amount of energy, then our velocity should be reduced. So simply speaking, the negative slope shown here, that is related with transition of our electrons from gamma belly to L belly. That is quite significant. Why do we have such kind of thing? Because the distance between gamma and L is not that high enough. If L belly is located far away from gamma belly, then we will not observe this kind of behavior. But unfortunately, the energetic distance is just 0.3 electron volt, quite much accessible to our electrons, accelerated electrons, and this is called as negative differential mobility, sometimes shorted as NDR. What's R? R is resistance. Okay. So now I think we have covered or prepared material about the mobility. And mobility, please note that once again, mobility is related with velocity, and the major motivation or driving force was the electric field. So we are considering always the case where we apply certain electric field. Then natural question is, then if we go to the exactly zero electric field case, then there is no way for us to generate electron in motion. If we don't apply any electric field, then no current will flow. If we accept only up to now, then that is the case. But everybody understand this is not the case. If we have a high density of electron, and if we have a low density of electrons, then they will move. So simply speaking, in addition to the so-called drift mechanism initiated by the applied electric field, we have an additional mechanism which allows the movement of our electrons. What is it? So as we all expect, that is called as diffusion. The difference is, once again, drift is initiated by the electric field. However, diffusion is initiated not by electric field, but by the gradient of electron density or hole density. If we have non-uniformity of electron density, then diffusion will occur. If we have non-uniformity of hole density, then diffusion will occur. How can you make this non-uniformity? It is quite simple. If you dope this part highly with n-type dopant, then you will have so many electrons. And here you have not so many electrons, then there will be certain diffusion mechanism. So that is not that difficult. However, there is also another way to make non-uniformity in the electron density. What is it? Another one is just to shed light. Photons are coming. Then inside this silicon material, they are interacting with silicon. Then this photon is now gone, annihilated. After that, inside it we have a generated electron hole pair. So this is actually used in our everyday life, in our cell phone. We have cameras, and it is using this phenomena. In silicon, when we have instant photon, that introduce certain electron hole pair generation. And think about this one. When we have photon, electron holes are only generated nearby the surface. Deep inside this silicon, since all of our photons are already observed in nearby the surface area, actually we have no excessive electrons, and here we have highly populated electrons and holes. Then there will be certain diffusion flux once again. There are other ways to generate, many different ways to generate imbalance or non-uniformity of electron density and hole density inside our structure. So I will explain this part in our next lecture on Wednesday. Thank you.